All right. In this video, I'm going to look at some examples of second order linear homogeneous ODEs of this form: ay double prime plus by prime plus cy equal to 0. In part 1 of this series, we've seen that whenever we have got this ODE, the characteristic or auxiliary equation is going to be quadratic, given by AR squared plus BR plus C equal to 0. Then if R1 and R2 are real distinct roots of this equation here, then the general solution is going to be given by A e to the R1x plus B e to the R2x, so A and B are arbitrary constants. If R1 is a repeated root of the auxiliary equation, then the general solution is going to be A plus Bx e to the R1x. If R1 and R2 are complex roots given by alpha plus or minus I beta, then the general solution is going to be e to the alpha x into A cosine beta x plus B sine beta x. All right, so let's look at some examples now. So in this set of examples, we are required to solve each. IVP stands for initial value problem, boundary value problem. BVP stands for boundary value problem. We already mentioned, if you check our video on introduction to ordinary differential equations, that a problem is called initial value problem if all the conditions are specified at one point. So for instance here, this condition is specified at x equals to 0. That one is also at x equals to 0, which means this one is an IVP. Same thing for this one. But for part C, first condition is specified at x equals to 0. The second one at x equals to pi. So that makes that one a BVP. BVP, this one as well. And that one is also a boundary value problem. All right, so let's have a go at the first one. So in the first one, we have got y double prime minus y prime minus 2y equal to 0. The conditions are when x is 0, y is 2, and then at the same point the derivative is minus 1. So the first thing we're going to need to do here is to find the auxiliary equation. Okay, so now notice that the auxiliary equation is just obtained by replacing second order derivative term by quadratic in R, first order derivative term by linear in R, and y is going to be replaced by a constant. So here we're going to have r squared minus r minus 2 equal to 0. This factors out to r minus 2r plus 1, which means the roots are 2 and negative 1. Okay, or maybe let's write them like this for consistency. That's r1 and that's r2. So this tells us that the general solution is going to be AE to the 2x plus BE to the negative x. Okay, then we need to apply the initial conditions to find the values of a and b. Now, since in the initial conditions we need y and its derivative, it's advisable to work out the derivative of y here. It's going to be 2ae to the 2x minus be to the minus x. Okay, then after that we're going to apply the initial conditions. Okay, so when we substitute, maybe let's write this like this. So when x is 0, y is 2. So we're going to plug in 0 here and here. It's going to give us a plus b. Y is equals to 2. So this is going to take the value of 2. Okay, so that's our first equation. Then the second condition, when x is 0, the derivative is negative 1. So again, we're going to plug in x is 0 here and here. So that's going to give us 2a minus b is equal to negative 1. Okay. So this is a linear system of simultaneous equations. We can solve this. When we do, we find... Alright, so solving this gives us a is a third and b is 5/3. So this is telling us that the particular solution is going to be given by 1/3 into e to the 2x plus 5e to the minus x. Okay, so that is part A. Part B, we have got 4y double prime minus 4y prime plus y equal to 0. When x equals to 0, the y and its derivative are both equal to 1. So it means this time the auxiliary equation is going to be 4r squared minus 4r plus 1. This factorizes to 2r minus 1 all squared, which tells us that we're going to have just one repeated root, and its value is 1/2. So the general solution is going to be a plus bxe to the x over 2, or 1/2 x. The derivative of this using the product rule, if we differentiate the term in the brackets, we're going to get b, and then if we keep the term in the brackets fixed and differentiate the exponential, we're going to multiply everything by 1/2. So this is just going to be b plus a over 2 plus bx over 2e x over 2. Okay, then if we apply the boundary conditions or the initial conditions, so In the first case, we let x to be 0 and y to be 1. Okay, so that means this will be 1, x will be 0, so that's a plus b times 0, and then e to the 0. So this is just telling us that a is going to be equal to 1. Then in the second case, again y prime is 1, so this is going to be 1. X is 0 again, so this is going to be b plus, remember we just found that a is 1, so this is going to be 1 over 2, and this term vanishes because x is 0. And then from here we find that b is equal to 1/2. Okay, so this is telling us that y of x equal to 1 plus x over 2 e to the x over 2. This is the particular solution for part B. Right, then now we go to part C. In part C we have got y double prime minus 4y prime plus 13y equal to 0. When x is 0, y is 0. When x is pi, the derivative is equal to 1. The auxiliary equation or characteristic equation is going to be r squared minus 4r plus 13. Solving this using the quadratic formula gives us 2 plus or minus 3i. So that means, let me just rewrite this. So what that means is that r1 is 2 plus 3i, r2 is 2 minus 3i. So if we put it in the context or the framework of what we have here, it means alpha is 2 and beta is 3. Okay, so that means our general solution is going to be e to the 2x not 2 alpha, e to the 2x, a cosine 3x plus b sine 3x. Alpha is 2 and beta is 3. Okay, for the boundary conditions, we're going to need the derivative of y. So if we differentiate this using the product rule, so if we just differentiate the exponential function, it's going to be this times 2. So 2a cosine 3x plus 2b sine 3x. Then if we keep the exponential fixed and differentiate the term inside the square brackets, we're going to get 3 times b cosine 3x is the derivative of this one, then minus 3a sine 3x, so derivative of cosine is a negative sine. if we collect terms, so this is e to the 2x, so the cosine terms just going to be 2a minus 3b, and the sine terms 2b minus 3a sine 3x. So that's going to be the derivative of y. Now then we're going to apply the boundary conditions. So the first one says when x is 0, y is 0. So that's here. So we're going to plug in 0 here. 0 there, 0 there, and 0 there. Okay. So apply 0 here, it just gives us 0. Cosine 0 is 1, sine 0 is 0. So this side is just going to be a. Okay. So a is going to be equal to 0. Because when x is 0, y is 0. So that first one gives us that. The second condition says when x is pi, y prime is 1. Okay, so we're going to have 1 is equal to e to the 2 pi. Now remember a is already 0. So this is 0 here. This is 0 there. So then we're going to have negative 3b cosine 3 pi plus 2b sine 3 pi. Okay. Cosine 3 pi is negative 1. Sine 3 pi is 0. So we're going to have e to the 2 pi negative 3b times negative 1, because this one disappears. And so from here we can make b the subject of the formula. Sorry, this should be like this because it's multiplication. So b is going to be 1/3 e to the minus 2 pi. Okay, so remember a is 0. So finally, so we're going to plug in a is 0 here, b is that 1/3 e to the minus 2 pi. So our particular solution, 1/3 e to the 2x e to the minus 2 pi e to the minus 2 pi here, and then this is all multiplied by sine 3x, which is this term here. Tidy this up. 1/3 e to the 2 is common, sine 3x. So that is our particular solution. All right. Okay. So that was part C. We are now going to give you an opportunity to have a go at D and E. So if you just want to have a go at D and E, you could pause the video, just pause the video, have a go at these two, and then you can compare with our solution when you continue the video. All right. We hoping that you have had a go at C and D. I'm now going to scroll down to our solution. All right, so for that's D and E actually. For D, the auxiliary equation is going to be 4 squared plus 1 equal to 0. If you solve this, we get plus or minus I over 2. So these are complex conjugates. In this case, the alpha is 0, beta is 1/2. So general solution will be A cosine x12 plus B sine x12. And that's going to be our derivative. So if we plug in x equals to 0, gives y equals to 0. So this is going to be 0, 0 here, 0 here. Just gives us A is 0. Then for the derivative, when x is power on 2, y is root 2. So root 2 here, this is y. Remember, A is already 0, so this term is out of consideration now. Then when x is pi on 2, it's going to be cosine pi on 4. Then cosine pi on 4 is 1 on root 2, which means that B is going to be 4. So our particular solution is going to be 4 sine x on 2. Okay, and then for E, the auxiliary equation is going to be r squared minus 4 equals to 0. So r1 is 2 and r2 is negative 2. And that's going to be our general solution with its derivative. So when x is 0, again y is 0. So going to plug in 0 here, 0 there, 0 there. Gives us A plus B is 0. So from here, it means that B is negative A, which we can substitute here. So that's going to give us 2A e to the 4 plus 2A e to the minus 4 is equal to 2. So this thing is going to be 2 is common, so it's going to be A e to the 4 plus e to the minus 4 equal to 1. If we divide this by 2, then this is just hyperbolic cosine of 4. Means A is going to be 1 all over 2 hyperbolic cosine of 4. So then we're going to plug this in here. So remember, A is negative B. So we can write this in terms of A as well. So y of x is going to be A into 2x minus e to the minus 2x, because B is negative A. So that becomes negative A. And then we've just said A is 1 over 2 hyperbolic cosine 4 e to the 2x minus a to the minus 2x. This, if we absorb the factor of 2 here, and then this term is just hyperbolic sine of 2. It's called the hyperbolic sine of 2x over hyperbolic cosine of 4. So that is our final expression of the particular solution. Okay, thanks for watching. Hopefully these are useful. You can subscribe so that you get notified whenever we post new stuff.